All right, so we're going to apply Atwood's machine equation, the acceleration that we determined from problem number 22. So here's my attempt to draw the diagram. You have two equal masses which would either stay at rest if they were already at rest or move with constant velocity until this little toad-like creature. And I drew a little blue stick figure there representing the little toad-like creature. Can't draw a toad, but so that my mass on the right is slightly heavier than the mass on the left. There's going to be two parts to this problem. In the first part, actually the heavy mass is going to accelerate down well, they're both going to accelerate. The little mass on the left will accelerate up, the mass on the right will accelerate down. And I don't have this to scale, obviously, and so forth, but bottom line is eventually this mass and the toad will get down a little ways. It says it's going to fall 0.5 meters, and then the little toad jumps off. So it gets down here, which is, okay, that's the 0.5 kilograms. So it fell 0.50 meters. And that's when the little guy jumps off. After that, then, once he jumps off, if there's enough rope here, we're assuming there's a lot more rope involved and nothing's getting hung up because the other one's going up. In other words, assuming that the mass on the left doesn't hit the pulley yet, the one on the right will keep going down. But now, after he jumps off, after the little guy jumps off, there'll be constant velocity, and the thing continues down another 1.2 meters. So down here even further. So this is that right-hand mass, and the little guy jumped off here in the middle. All right, and this is another 1.2 meters. 1.2. Now, I'm going to focus on the second part right now, part 2, doing it backwards, because in part 2 we have constant velocity. We have v, which is, well, we don't know. S is 1.2 meters. This is a little bit overkill right now. And t is it's 3.0 seconds. So 3.0 seconds. So we know v equals 1.2 divided by 3.0. So v during that constant velocity part is 0.4 meters per second. That's the constant velocity. Well, then that must have been the final velocity before the little toad jumped off. So that was part 2. I never put the 2 up here. Part 2. But part 1 now, kind of playing this backwards, let me switch to red. Part 1, while the toad is still on there, the toad-like creature, it's accelerating down, where the v initial of the whole system, we're just concentrating on the right-hand mass right now, v initial is 0. V final for that mass with the little toad on it down is 0.4 meters per second. A is what we're looking for. S is technically negative 0.50 meters. You don't need to put the negative in there, but I'll be consistent with other problems. And t. All right, so we have enough information to figure out the acceleration of this particular system, the mass on the right, and it's also going to be the same acceleration for the mass on the left going up. But bottom line here is if we use the fourth uniform acceleration equation, and that is v sub f squared equals v sub I squared plus 2as, that would be 0.4 squared equals 0 squared, plus 2 times what we're looking for, a, times 0.5. And 2 times 0.5 is 1. And 0.4 squared, I believe, is 0.16. So the acceleration is 0.16, and that's meters per second squared, because I did everything in meters and seconds. So that's the acceleration of this system. But we want to have the acceleration on the planet Mongo. Well, all I do now is plug that into this upper equation at the very top of the page. And I know the two masses. Well, be careful here, because mass 1, mass 2 is the bigger mass. The mass 2 is the sum of the 0.25 plus the little Granch. So let me switch to blue. So you're going to plug in, well, mass 1 will be just the mass on the left, which is the 0.25 kilograms. You're going to plug that in. Mass 2 will be the 0.25 plus the Granch, which is 0.025. That gives a total of what? 0.025 no, 0.275. So that gives you 0.275 kilograms on the right hand. So you're going to plug in m sub 1 is 0.25, m sub 2 is 0.275, and the value for A at the bottom here, the 0.16, and solve for G on Planet Mongo. Good luck.